In chapter 22, it's all about putting groups on benzene. A very important skill. If you look at any pharmaceutical out there, almost every one of them, more than 99% of pharmaceuticals have at least one benzene in them. And they've always got groups on them. So putting groups on benzene is very important in pharmaceutical synthesis and pharmaceutical science. So here's our deal. Well, that's activity 1. You need activity 2. And what we're going to do with benzene here is put a methyl group on it. And the conditions you need to do that are such that you need a methyl with a halogen on it, and this catalyst, aluminum chloride, looks like a catalyst on this page how many times? 3 times. Every time you see aluminum chloride, what kind of group are you putting on the benzene? A carbon group. Whether it's a methyl or a tert-butyl or an acetyl in this case. It's an acetyl. In general, it's called an acyl group. If that was an R, you can call it acyl, and that covers everything. Not alkyl, that's acyl. And so that's called the acylation of benzene. This specific one where the R is a methyl, here R equals methyl. So you can call it a more specific acetylation. Oops. Acetylation is the process that you would use to put an acetyl group on benzene. So that covers those 3. And these are both alkylations. And it was the same 2 gentlemen that came up with all of these reactions. Well, their graduate workers did. And their names were Friedel and Kraft. It was Otto Friedel and, oh, I forgot Kraft's first name. Was it Han? Sorry, Han. Or... Okay, so we have the Friedel-Crafts alkylation, Friedel-Crafts acylation. And we're also going to look at nitration. Nitration. That's a nitro group you put on the benzene right there. Process of putting it on is called nitration. So I want to show how general the alkylation and acylation are. So I'm going to start all 3 of those mechanisms right now the same way. One thing I didn't say yet is that it is hard to put groups on benzene. As we discussed last day, benzene has unusually stable pi bonds because of that aromaticity phenomenon. It really helps those pi electrons be more stable. So to get them to react is not easy. So even though I have a reactive electrophile here, that's an electrophile, it wants to be attacked by a nucleophile. Benzene's not a good enough nucleophile. So what I'm going to do is I'm going to change this electrophile temporarily into a nucleophile. What? I mean, you can't do that, can you? You can force something that normally likes being attacked to be an attacker by adding something that really is deprived of electrons. Aluminum with 3 bonds to more electronegative chlorine is it's hot. The aluminum 3+, it wants electrons desperately. It'll take them from anything. I'll do a demo in lab in Orgo 1 lab where I take aluminum chloride and add water to it. And it smokes. And I do it in the hood because if you smelled it, you'd smell HCl being formed, and that burns your nose. You don't want that. So it's nasty. So here's how nasty aluminum chloride is. It can make the lone pair on chlorine reactive enough to attack the aluminum. I've used red circles already. I apologize. I'll go to a rare pink arrow here. Aluminum and boron are the same. Their nature is to alternate between 3 and 4 bonds. That's what they do. They're little machines. Right now it has no charge and 3 bonds. And we're going to finish with a more bonds, which is more stable, but a charge, which is less stable. So that's why it does what it does. It's got good and bad either way. It's got an octet violation before we make the bonds, and it's got charges after we make the bond. So what you have here is CH3 attached to a Cl, attached to an aluminum that now has 4 bonds. That makes the aluminum a minus, and a chlorine with 2 bonds is a plus. Similar story down here. We're going to have a tert butyl, a little chicken foot with a Cl, an AlCl3 here. And similar story here. Oh, we're going green, lost the team. We're going to have a CH3 carbonyl Cl. Oh, I forgot my plus charge over here. Formal charge police are here. And we have AlCl3 on here. Minus and plus. So every time the chlorine becomes a plus and the aluminum becomes a minus with a 4th bond. There's something that can happen with this second one that can't happen with the first one, and I'm going to show you right now. The second one can do this, the first one cannot. Please ask yourself why the first one cannot do this at all. If you did it on the first one, you'd lose points. It'd be sadness. We don't like sadness. If you did this same mechanism over here, you'd generate a methyl cation. I don't believe I even said it. You're not allowed to make a methyl cation or a primary carbocation. They're haram. Don't make them. So this mechanism stops here before the next step. This one proceeds to make a nice tertiary carbocation. And this one makes a weird ion called an acylium. Hey, we got that acyl. We're working this acyl prefix heavy right now. Lone pair on the oxygen comes down, forms a 3rd bond, and kicks off this guy. And it goes down here, and you've made an acylium ion. I'm going to flip it a little bit. It's called an acylium ion. And you get the same aluminum every time. Where's my favorite one? This one right here. Oh, I don't like that. I'm going to draw it. Plus Cl attached to AlCl3 with a minus. We're going to use that later. You know you have to use that later because I told you aluminum chloride is a catalyst. You better be remaking aluminum chloride pretty soon, right? That's one good thing you know, when you have a catalyst, you got to remake that catalyst somewhere in the mechanism. It's a theme that's always been there. All right, it's time for benzene to be a nucleophile. Every reaction today, up until the very end of the day, is in this broad category called electrophilic, aromatic, substitution. And this is for Ali, short form, EAS. There you go. Okay. And what happens during EAS? Well, we're going to put an aromatic nucleophile attack an electrophile. Here's your electrophile. Can I highlight the electrophile? Have I used highlighter here except for EAS? Here's the electrophile here. Here's the electrophile here. And our psyllium ion is the electrophile here. Benzene attacks those. Leaving group leaves. That's like a backside attack, isn't it? And this one, I'm going to need 2 copies of my molecule because I have 2 products and they go on different positions. I hope you can see that, right? So I'm going to need 2 toluenes to do this mechanism and 2 tert-butyl cations. So here's just a second copy of toluene. Second copy of toluene. And I'm going to use that tert-butyl over there. And I'm going to do a sneaky move on you here. I don't like when I do this either. I'm moving everything down. So I can use the top of my screen. So I'm going to have this one attack in the ortho position the tert-butyl group. I know. I heard the chuckling. How the heck am I going to get that on my quiz that doesn't have room on the top? You can flip it over if you want. So I just need to attack that with this pair of electrons. I hope it's clear that to make this product, you should use this pi bond. To make this product, you should use this pi bond. Look where the group is. And to make this product, you should use a pi bond that attaches to the para-carbon, because there's a group on the para-carbon. You better use this pi bond. So top one for the ortho, I need this to attack the carbocation. And bottom one, I need the ortho position. No, that was the ortho. The para position to attack the carbocation. And you're going to generate intermediates here. The intermediates are as such. We're going to have, here's the things that didn't change. Still got a methyl up there, still got a double bond here, still have a double bond here. We got a new tert-butyl group on the ortho position. The position with the methyl lost a bond, didn't replace it. What kind of carbon is that? Used to have 4 bonds. Now it's only got 3. That is a world famous carbocation. Quite stable. It's tertiary and allylic. And I'd like to point out that there's an H right here. Yeah. That was there from the beginning and is not there in the end. Not there in the end. That has to go away. And your catalyst has to reform. Where's the part with the catalyst? It's here. ClAlCl3 minus. We're going to have everything happen that we need to happen here. We have Cl attached to Al. Cl3 minus. The Cl is going to come off with its electrons and grab the H in a very fast reaction called E1. In this case, the E1 is so fast because it's taking a molecule that wasn't aromatic. Re-aromatization is not with a C there. Ation. Fast. Anytime you make something aromatic that wasn't fast. Good. So that gives us the ortho product. Ortho. Ortho will be minor. Para will be major. For reasons of steric hindrance, tert-butyl group starts bumping into the methyl if you put it ortho, or as it's approaching, it's getting close to bumping into the methyl. No such problem in the para position. Let's do the para mechanism, shall we? We've attacked the cation with the para pi electrons. The para pi electrons, that's hard to say. The pair of pi electrons that were on the para carbon. And what we have here is a methyl on a benzene that still has that pi bond, still has this pi bond. And we have a new tert-butyl group down there. We have an old H on here. And you have a cation on the position that lost the fourth bond. And this has to become, choose a color that shows better. Has to become that somehow. And look at that, the catalyst precursor is right above it. How handy. Cl comes off and grabs the H. Sigma becomes pi, E1. ... Fast. Same comments as before. And we're making the pair. Yeah. What else did you make? Well, you made your catalyst and HCl. You want to show that? You don't have to. HCl plus AlCl3. And a keyboard. Don't know how I made the keyboard. There you go. Meow. There you go. Catalyst is back. That's why. You don't have to show me those products. But they happen. What do we know so far? We know how to put a methyl group on. We know how to put a tert-butyl group on. And eventually we're going to put a ketone on. That's down here. Ketone. You ready? We've made our psyllium ion. And how do we get that to, it needs to go here from here. So we're taking this guy and making it into this guy. Which pair of pi electrons do we have to use on the benzene? Well, you got to find where the new group is and where the pi bond is and say, okay, that had to be the pi bond that was here. That's the one that broke to make the bond. So it's coming to the psyllium ion. There, right to the carbon. Pi breaks. And the ketone's formed. What else is formed? Let's see what we're doing here. Let's go with blue, green, something. So we've got a benzene that's no longer a benzene. Didn't use this pi bond, didn't use this pi bond, kept the tert-butyl, kept the methyl, made a new bond to this position. The methyl moved because I have trouble rotating things myself, don't I? There you go. I'm sorry. Take a second, make sure you move the methyl over if you were keeping up with me. This is a rotated version of this molecule. We're here now. New bond is here. And it's to a carbonyl that has a methyl on it. The old carbon here, oops, The old carbon here had an H on it. There was no H on here. There you go. The adjacent carbon has a C+. The other carbon that didn't get the group lost a bond. This carbon here, the one that doesn't get the group, lost a bond, so it's got 3 bonds. It's a cation. And we need to make this into our final product. Same way as the other 2 times, sorry. The chloride comes off the aluminum trichloride anion and picks up a proton. The chloride comes off the aluminum trichloride anion, picks up this proton. Sigma becomes pi. I'm just going to say fast here. This is real fast. Re-aromatization is always really fast. And you got the same 2 things, HCl and your meow, aluminum trichloride or aluminum chloride. Okay. We're going to do nitration next. Nitration. Okay. So in nitration, we have to generate a different electrophile, obviously. There's no carbon. It's all about generating an electrophile and attacking it with an aromatic ring. The title kind of implies that. Generate an electrophile, attack it with an aromatic ring. So here's our nitric acid. I know it doesn't look like nitric acid. Usually I have it drawn out. In fact, I think it's the only time I don't have it drawn out. This will be the form I put it on the test. Right there. Because it, it helps you with the mechanism. We got to make the OH leave. We got to lose water in this thing. I know there's not water to lose, but we're going to make it lose water. Makes no sense. If you give that O a proton, then it'll have 2 H's, and it can leave as water. So where's it going to get a proton from? It's going to get it from sulfuric acid. Sulfuric acid is such a strong acid that it can force nitric acid to be a base. That's exactly what's going to happen here. In fact, it's happening. Those arrows, nitric acid is picking up a proton. It's not nitric acid. It was, but it's acting like a base. That's a theme today on every reaction here. You took something that was already an electrophile, either a Lewis or a Bronsted electrophile. Those are acids, by the way. And you made them behave like nucleophiles because you had an even stronger electrophile present with them. Sulfuric acid is a stronger acid than nitric acid. Aluminum chloride is a stronger Lewis acid than terbutyl chloride is. Aluminum chloride here is a stronger Lewis acid than methyl chloride is. Okay, so after you do that, then it's gonna dehydrate itself. So we're just on this last one, red first. That's to make it a better leaving group. And then blue second. And here it comes. Lone pair kicks in, leaving group leaves, and you've generated your nitro electrophile. Here it is. You want to see it? Of course you do. Where do I need it? I need it somewhere down here. There's your water. Okay. There's your electrophile. You are responsible for making all of these electrophiles today and then reacting them with benzene. And let's see. We're taking only that top product. So what pair of pi electrons on that top product? This one is going to react to make this. Well, you got to find the position where the new group is. And it has to be the pi bond that was there. That's the only pi bond you should use here. Here it comes. Here it comes. Make a fifth bond, compensate by breaking the fifth bond. And there we go. Sneak it over here. And you're going to get the benzene. It's no longer aromatic. Didn't touch that. Didn't touch that. Didn't touch this. And put a new NO2 on. This is the nitro group. Right now, reminder, where the new group goes, there was an old H that has to go away. The other carbon of the alkene is a cation every time. Don't get those backwards. That's the only H that has to go away, right there. And go purple. Gonna make that into that. What's gonna grab the H? Well, you know, I didn't show my sulfate ion. How convenient, it's showing up now. I think that's our best base in this one. For the very fast step at the end here. Can somebody tell me why it's so fast? Anybody? This last step in all four of these reactions, why is it so fast? It's making aromatic from something that wasn't aromatic. Good answer. And there's the big picture. If we can get it all on one screen. There we go. Well, we didn't because the top got cut off. And we're going to end the video. I think we have everything we need.